All right, so by definition, we say that a transformation is linear if it holds the addition property indicated here and it holds the scalar multiplication property here. And we'll show in our first example kind of what that means with the scalar multiple and then also with the addition here, okay? So every matrix transformation that we're going to do is a linear transformation. And more important examples of these that are not matrix transformation will be discussed later on in the course. Okay, so we say that the operations of addition and scalar multiplication are preserved. And that's what, like, a more official way to say these things are met. So let's go ahead and look at this one here. If T is a linear transformation, then it must be true that T of the zero vector is 0. And the reason is because if you had anything else inside of there, like 0 times x, then based on this scalar multiple rule right here, I should be able to take that outside. And so I'm going to end up getting 0 on the outside when I multiply, okay? And then it also is true that if you have some kind of combination of scalars and addition, that you can kind of apply both rules at once. Also, observe that if a transformation does satisfy this right here, then it has to be a linear transformation by what we've been talking about this entire time, because TU, TV, like those would end up making vectors, and so this must be true, or if you apply a transformation on a set of linear systems, or a linear combination, then you're going to end up getting those C's out in a linear combination of the transformation, okay? All right, let's look at example 4. So if I just have some scalar R and the transformation is R2 into R2. So let's remind ourselves what that means. That means I'm taking something x1, x2, and I'm just mapping it into, let's say, AB. Okay? And so that transformation with that scalar R is R times our x vector. So R times the x vector means that we're going to end up getting Rx1, Rx2. Okay, that makes sense. Okay, so it's called a contraction when R is between 0 and 1 because it's going to make it smaller, and it's called a dilation if R is bigger than 1. So let R equal 3 and show that this is a linear transformation. So if it's a linear transformation, then what needs to be true is that T plus Cu plus dV must be equal to CTU plus DTV. And what that does is I'm using this step here that I starred instead of doing these two steps here in the definition separately. Okay, so I'm going to show this is true by doing both the scalar multiplication and the addition, okay, all kind of in one versus having to do that as two different steps. All right, well, let's think about what T of Cu plus dV would be. Well, remember our transformation of vector x is 3 times vector x. So in this case, this is vector x, so that's 3 times Cu plus d, vector v, because of distribution properties. This is 3c times vector u plus 3d times vector v. But then I can also kind of move this around because of multiplication properties and say that this is c times 3 vector u plus d times 3 vector v. Well, let's think about up here, what does it mean to be t vector u under this transformation? Well, that means to be 3u. What does it mean to be t of vector v? Well, that means to be 3 vector v. So I can replace 3tu with t vector u, because 3u is just the transformation of vector u under this scalar multiple of 3. Plus, same thing here. So anytime it says show that this is a linear transformation, you are going to write out this piece right here and work through algebraically in order to prove that the left-hand side equals the right-hand side. Sometimes it is easier to go from the right to the left or left to the right, just depending on what's given to you, but that's where you're going to start. You're then going to apply the transformation that's given to you, that's defined in the problem, and then show that one side is the same as the other. All right, let's look at example number 5. Define a linear transformation from R2 into R2 such that we have this. Now let's break this down just a little bit. That means then, remember, t of x is a times x, just in general. So that means that my vector A must be, or my matrix A, I should say, must be this. And then here's x. And what it ends up doing is it ends up reversing your entries, and the negative goes on top. So let's find these images under t of u. So t of u would end up being -1, 4. Okay. T of v would end up being -3, 2. Let's do one example of like what we're doing by applying that rule that was given to us. So 4, 1. All right, 0 times 4. Okay, 0 times 4 minus 1 gives me -1. 1 times 4 plus 0 gives me 4. And so that is why I end up getting this here, but I'm just using the fact that I know my outcome has to switch. Okay, and then the last one says to do u plus v equals 6/4. Well, let's show this. Let's show that t of u plus v is equal to t of u plus t of v. Because this is a linear transformation, so it should make sense that you can apply it this way. All right, well, t of u plus v is going to end up giving me -4/6 by this rule. Okay, switch and make the top one negative. Is that equal to, well, we already found t of u, which was -1, 4, division bar, plus -3, 2, and you can check, and that is true.